Good morning, and thank you so much for attending today's session. We're going to give it just a couple more minutes for the remainder of the folks to jump on, and we'll kick things off around 10:03. Good morning. If you're just jumping on, we're going to give it just a couple more minutes. We'll be kicking things off at 10:03. Hello and good morning again. If you're just joining us, we'll be kicking things off in just a minute. All right. Thank you everyone for joining us this morning to learn more about FortiAP and FortiSwitch best practices. My name is Soraya Tati, and I am the Fortinet Secure Specialist covering the West Coast. And presenting today is our Secure Access Engineer, Mr. Eric Scholhoff. So Eric and I are part of an overlay team here at Fortinet supporting the FortiSwitch, FortiAP, and FortiExtender. That's our 3G, 4G backup solution. This product line actually makes up over 25% of Fortinet's overall revenue and is the second fastest growing business unit outside of the FortiGate. If you like what you're seeing and are interested in learning more, please reach out to me or your Fortinet team and we can schedule a time to chat further. So before I hand things off to Eric, I want to touch on a few housekeeping items. So we do have a lot to cover today in a short period of time. So if you have a question, please submit them in the webinar chat window. What we'll do is try to get to them throughout the webinar. If we're unable to address that question, we'll send a follow-up email after this recording. Also, Eric is going to give you our email addresses. You can also reach us directly. He'll be showing our addresses at the end of this presentation. This session will be recorded and sent in a follow-up email at the end of the week. So thank you so much for your time this morning, and I hope you enjoy today's presentation. Go ahead and take it away, Eric.
Thank you, Soraya. Thank you for kicking this off, and thank you for giving me an opportunity to present on one of my very favorite topics, wireless and switching best practices. I've been a secure access systems engineer here at Fortinet for over 7 years now. Working with the wireless products and now switching products as well. So it's a subject that's very dear to my heart. I've deployed a large number of Fortinet wireless networks and switching infrastructures over the years, and I'm very happy and very eager to share what I've learned over the years with everyone. Getting started with a wireless network. All good wireless networks have to start in the planning stage. You definitely must plan ahead for the desired outcome. Getting started, what is the purpose of the network? Is the network going to be a wired replacement where you're going to ditch the switches, get devices off the wired onto the wireless network, enable mobility throughout your work area? Or is it going to be a simple hotspot, a best effort type network where you throw up some access points in coverage areas, and then any ability to roam between those coverage areas or have high performance is a secondary feature? What type of applications are you going to be running on the network? Is it mission critical, or is it a high bandwidth application that requires high performance? Or is it, again, a best effort low bandwidth application using maybe barcode scanners in a warehouse, very transactional? Or is it high performance and critical medical devices and cameras streaming video? The different applications and the different purpose of the network will definitely affect how we design the network and how we plan for the network. If I'm doing a high performance, high bandwidth, a wired replacement type network, I'm going to design the network for a -65 signal strength everywhere in 5 gigahertz. And that's going to provide, as we're going to see later in the presentation, excellent performance and maximum bandwidth and performance to the devices. If it doesn't need that type of performance, then I might design to a lower standard. I might design to a -72 signal strength or better in the coverage areas. And we're going to take a look at what those numbers mean as far as the performance of our network. Some of the things we need to discuss is the device density, because the density of devices on the network will definitely affect how we design and plan for the network. One of the common questions I receive all too often is the same question people were asking 10 or 15 years ago about your access point. The question is, how many devices can I connect to your AP? And this is a very interesting question because the number of devices that you can simply connect to the access point, that is going to be a function of the chipset you're using. So if you're using a Qualcomm Atheros chipset or a Broadcom chipset on the access point, that chipset is going to have a maximum number of wireless devices that it allows to simultaneously associate to it. And that might be a very high number. That number might be 256 devices or 512 devices. And sure, you can use that number in marketing materials or in a data sheet to say our access point can support 512 devices. But what can those devices actually do with 512 of them associated to a single radio other than maintain a connection to the access point? This chart gives you a little bit of background and information on how many devices you can commonly use on a single radio on an access point and what type of applications that will support. So for cable replacement, when you want to give a gigabit Ethernet style feel to the network using wireless, you're going to want to keep that number of simultaneously associated devices on the radio quite low. As you move up to, for example, a classroom where you're going to have an access point in every classroom, and you're going to have 20 or 30 students that might have 2 devices each in very close proximity to the access point, we can increase that number to 16 to 25 devices per radio. As we go up to lower bandwidth applications, then we can allow that number to soar because the transactions are smaller, less bandwidth intensive, and we could get to those numbers of 50 or 100 devices per radio and support those applications. Another discussion on the signal strength, what signal strength to plan for. As I had mentioned previously, when I design a network for high performance, I want to have a -65 or better signal strength throughout the network. And what that means is what we see here. -65 is going to provide high data rate, full bandwidth available to the devices and the applications that use it. As the signal decreases through the -70s up to the -80s, your performance will decrease. And then as you hit 80 and lower, that's when you can start to expect those problems, slow page loads on a web browser application, and maybe some ping loss. So definitely have a goal in mind of what signal strength you want to see throughout your network when you go into that planning stage. As you plan your network, let me introduce you to some of the adversaries that I commonly see on wireless networks. These guys will rob you of your wireless network performance if you let them get established in your network. They are low RSSI, low signal strength, low data rates, interference, and then old technology. So old technology on your network, it may feel like an old friend on the network and someone that you've known a long time and you have good memories of 802.11n, but old technology is going to drag down the performance of your network. So try to eliminate that from the network. How do you plan your network? With Fortinet, we have a wireless network planning tool called Fortiplanner. Fortiplanner allows us to import a floor plan of your network in a JPEG or a PNG format into the application. It allows you to draw the interior and exterior walls in different materials. So you can draw walls that are glass or regular drywall or concrete. And then you can place access points in different locations, and you'll get an immediate depiction of the propagation of the signal, both in 5 gigahertz and 2.4 gigahertz. All the Fortinet access point models are available in Fortiplanner, so you can select exactly what model access point you want to build the network on, place it on the map, move it around as needed, and get a measurement of signal everywhere. And it provides an easy to use, once you're used to using it, and free to download tool to design your Forti-Access Point network. Considerations when using Fortiplanner, and this actually happened to me. You want to use the best, most accurate floor plan that you can get. So you want to try to avoid a floor plan that's written on a napkin that is totally unscalable. To get a good result, you need an accurate floor plan. You need to be able to scale it, and you can scale it based on a door frame, which is usually 3 feet, or a stairwell, or preferably there's actually a scale on the diagram that you can use to most accurately scale it. Gain some knowledge of the building materials. So all the walls might look the same on the floor plan, and it'll help you to have an accurate outcome if you know what the materials on those walls are, which walls might be solid glass, what's drywall, what's concrete, etc. Best practices in Fortiplanner, things I like to do that have ensured a positive outcome for me. I like to build in some wiggle room on the transmit power of the access point. So this lets me have some room in the event there's something that I didn't see or I didn't select a perfectly accurate wall material. So I like to reduce the transmit power on the radios on the access point in Fortiplanner by 3 dB to give me some room. I always start by analyzing the floor plan, and I like to put access points in the most important locations first, and then fill out through the less important locations. Some of those important locations are conference rooms. I always start by putting access points right in the conference rooms. I don't think there is any better strategy than to put the access point right where the users are. So put them in the conference room, not in the hallway next to the conference room. Also, executive offices. Many times on the floor plan, it'll be marked where the CEO's office, the CFO's office is, and I think it's a good strategy to put the access point right there, because those are the people paying the bills and the ones you want to be most pleased with the performance of the wireless network. Design for a specific RSSI through the deployment in 5 gigahertz. So the 2.4 gigahertz radio, it will travel through walls and obstacles and over distance better than the 5 gigahertz does. So I always design the network for 5 gigahertz, and then I know that my 2.4 gigahertz signal is actually going to be stronger than the 5 gigahertz. And then it allows me to design the network just once, not to have to design it with 2.4 gigahertz and then look at 5 gigahertz and see that I've spaced my access points too far away for 5 gigahertz and I don't have signal everywhere. Let's talk a little bit more about performance versus coverage. This is just a depiction here, but this is how the access point and the RSSI and the signal strength propagates. So as you see in the middle black space, that's where my access point is located. And within a very close range of that access point, I'm going to have very high signal. So this is when I'm about maybe 6 feet away from the access point. I'm going to have a signal in the -50s or -60s. It's going to be very strong. And then as I start to move out from the access point in concentric or roughly concentric circles, the signal strength is going to start to go down as I venture further away from the access point. And then you see the data rate I'm achieving is directly tied to the signal strength. So as my signal strength goes down, my data rate goes down. And as my data rate goes down, the performance of that entire cell, that entire access point, goes down with it. So as you see, as I go from a -60 signal to a -70 signal, my data rate is going down about 75%. I go from this theoretical 876 megabits per second down to 216 megabits per second. And then every packet that I transmit at that data rate takes 4 times longer to send than it would at 876 megabits per second. And what you need to keep in mind is this can happen within a pretty close proximity to the access point. You could go through this much change in your signal strength within just 25 or 30 feet of an access point. So keep that in mind while planning for your signal strength and performance. The next step in planning your network is to select the correct access point for the job. If deploying at a hotel or in a dorm room or a home office with a small number of users and devices, then a single radio access point might be a perfect solution for that. As we move into more challenging, higher density of users, higher performance applications, then we need to adjust the access point that we're going to use accordingly. So the first question is, how many radios? Is a one radio access point adequate, or do you want to have a 2 radio access point? When you get a 2 radio access point, then you get the benefit of being able to have a 5 gigahertz radio and a 2.4 gigahertz radio, and use both those spectrums efficiently for your wireless devices. I would say about, I don't know, 99% of the access points that I've sold have been 2 radio models. Additionally, now we've introduced several 3 radio access points, and that 3 radio access point might allow you to have 2 5 gigahertz radios simultaneously broadcasting on different 5 gigahertz channels, and then the 3rd radio on 2.4 gigahertz. Or you might want to use a 3rd radio as a monitor radio to do wireless intrusion detection on your network. So you definitely want to select an access point with the correct number of radios for your application. However, radio count isn't the only consideration. You also want to consider the functionality and the features supported on the access point. One of the features to consider is the MIMO and how many streams of data that the access point supports. We have 2x2, 3x3, and 4x4 MIMO access points. When you double the number of streams, when you go from a 2x2 access point to a 4x4 access point, that will have the effect of doubling the data rate and potentially doubling the throughput on that radio. So a 2x2 MIMO access point might be ideal and absolutely fine for a warehouse application. In a warehouse application, you might want to deploy a large number of access points at a low cost, and the bandwidth and the throughput is less of a concern. So the 2x2 data rates are absolutely fine. However, when you get into higher performance, you might want to take advantage of a 3x3 or 4x4 MIMO to increase those data rates and increase the throughput of each cell. Another thing to be concerned with and aware of is the standards that the access point supports. 802.11 AC Wave 2 is still a very popular standard and very commonly deployed. And it's typically absolutely fine to deploy these today in almost every environment. However, 802.11ax has been released. And if you do choose to deploy 802.11 AC Wave 2, when 802.11ax clients become more prevalent on your network, you're not going to be able to take advantage of all the improvements in 802.11ax on your network. Now that we've selected the access point that we're going to deploy, we do also have to plan for the Ethernet side, for the backhaul from the access point to our switch network. After all, we don't want the Ethernet to become the bottleneck. If we take a look at some of our popular access points, some access points, those 2x2 access points, or those single radio access points, historically have had a single gigabit per second Ethernet interface. So this interface allows you to connect the access point to a PoE switch. The PoE switch or injector will power the access point, and then we can backhaul 1 gigabit per second of data from the access point back to the switch network. On some of the higher performance access points, we started introducing dual gigabit Ethernet interfaces. So we have 2 gig interfaces here. And these allowed us a couple options on how to deploy them. They could be deployed as an active and a backup interface. So they could power the access point from both interfaces, have one be primary. If that one should go down, then the access point could switch over to the secondary interface without having to reboot and power up. More commonly, we would link aggregate those interfaces, and that would allow us to have a single 2 gigabit per second backhaul from the access point to the switch. And currently, on our highest performance 3 radio 802.11ax access point, we've introduced an mgig 2.5 gigabit per second interface on those switches. They also have a second 1 gig interface. So if we wire just the mgig interface to an mgig switch, we can backhaul 2.5 gigabit per second from the access point to the switch so that the Ethernet does not become a bottleneck. If we want to link aggregate those 2 interfaces, then the mgig interface will operate at 1 gigabit per second, but we can still get a 2 gigabit per second connection back to the network. Of course, if you're going to use the 802.11ax access point and you're going to backhaul it with a 2.5 gigabit per second interface, you need to make sure that you have switches that are going to support that interface. Next on our list is channel considerations. And let's start by talking about 2.4 gigahertz. And you remember this guy up in the right-hand corner here. This was old technology. In 2.4 gigahertz for Wi-Fi, we're only allotted about 72 megahertz of total spectrum. And what we've done commonly in 2.4 gigahertz is carved out 3 non-overlapping 20 megahertz channels. And in 2.4 gigahertz, we say that these channels are centered on channel 1, channel 6, and channel 11. As you see in the depiction here, if I have 3 access points, one using channel 1, one using channel 6, and one using channel 11, they can be operating in the same overlapping area without causing any interference with each other. What happens, however, when I go to deploy access point number 4, I've run out of channels to use. So I need to start reusing channels, and I have to put the 4th access point on channel 1, channel 6, or channel 11. So in 2.4 gigahertz, being an older technology with less spectrum, I am very hand-tied on how I can deploy my access points and still gain performance. This problem goes away with 5 gigahertz, and that's why 5 gigahertz is the spectrum and the network that we want to design our network for and where we're going to gain performance. What you see here on the top is all the individual 20 megahertz channels that are available in 5 gigahertz. So I have about 24 different 20 megahertz channels that don't overlap. So I could deploy 20 access points in a warehouse or in a convention center, each on a different channel, before I have to reuse any of those channels. However, to improve performance in 5 gigahertz, we can bond channels together to make a larger channel. And every time we bond a channel, for example, when we bond two 20 megahertz channels together to create a 40 megahertz channel, we are again doubling the data rate and doubling the potential throughput on that channel. So as you see, as I go to 40 megahertz wide channels, I drop my 24 channels down to 12 usable channels, but the payoff is I've doubled the potential throughput on those 12 channels. I can again go to even wider 80 megahertz wide channels. With 80 megahertz wide channels, I have 6 that I can use. So again, I've cut the number of available channels in half. But again, as I go from 40 to 80, I've doubled the potential data rate. And with our latest access points, we even support on some of the access points the ability to bond multiple channels together to come up with a 160 megahertz wide channel, which is a huge channel. And as you see, just using 260 megahertz wide channels is all the channel space that's available in 160 megahertz for channel bonding. So selecting the correct channel width for your application can dramatically alter the performance of your network. If you use too narrow of a channel, then you're capping your performance, and possibly you're needlessly capping your performance. If you go too high, you risk introducing our friend interference into your network. So let's take a look at this exercise here. Here I have 8 classrooms. They're across an open space from each other. We're going to put an access point in each classroom. So I'm going to have at least one wall, typically multiple walls between one access point and the other. What size channel width would we use here? I would recommend using an 80 megahertz wide channel here. So while I have 8 rooms, the 80 megahertz wide channels provide me with 6 high performance channels I can use. I can reuse a couple of those channels once each and still have ample separation from those access points. So I'm getting high performance. I'm not increasing interference at this point because I have good isolation between those APs. An additional tip on this deployment, since it's an AP per classroom, and I know that my room is fairly small and that all my wireless users are tightly grouped around the access point, I can actually turn down the transmit power on my access points since I don't need to go through the wall to the next classroom to provide coverage there. And that will actually further reduce the likelihood of interference on that network. Here's another exercise here of what channel width to use in a warehouse. Now this warehouse is a large open space. I don't have any walls between the access points. I might have racks and I might have materials on the racks that will provide some attenuation, but I don't necessarily know what the level of that attenuation is or if it's going to change over time as different products get put on the racks. I might need possibly 16 access points to cover this space. So what channel width should I use? In this case, I went with the small 20 megahertz wide channels, and that provides me the maximum number of channels, minimizes my my interference and my requirement to reuse channels. Typically in a warehouse, it's a low bandwidth application. I might be doing inventory with barcode scanners, and I don't need the performance of a 40 or a 80 megahertz wide channel necessarily. So I can get away with using a 20 megahertz wide channel here. So how do I manage this channel allocation? As you see here on this diagram, I had to manually go in and decide exactly which access point I wanted on which channel and how to space them out to avoid interference and channel reuse. On the FortiGate wireless controller, we have a feature that does this for you. It's called DARP, or Automatic Resource Radio Provisioning. And it is automatic channel selection. So what the DARP will do for you when we turn it on in the access point profile, then the access points will scan the air at an assigned interval. They'll look at the channels that are currently in use by other access points, and then they will select their best channel based on what they see. And then you can create a schedule for them to revisit that decision and make any necessary adjustments should a better channel become available for them to use. That will greatly reduce your management overhead and your configuration as you deploy the network. Just turn on the DARP and let the access points make those decisions for you. And how do you determine exactly how good of a job it did, and how busy are your channels, and how busy is the medium overall? The access points in the FortiGate are always scanning, taking a look at the channels and the spectrum and how busy those channels are. This information is shown to you both in the web interface on the FortiGate and even from the CLI of the access point. So here you see it shows you channel 36, utilization on that channel is 51%. That's a fairly highly used channel, whereas channel 40 and 44 are at 5% and 3%, and that's more of a typical number to see on 5 gigahertz. Down at the bottom, it shows you 2.4 gigahertz channels, and you see channel 11 is utilized 73%. So you know that channel 11 is fairly high utilized, and if you have to put another access point on channel 11, there's not a whole lot of airtime, a whole lot of throughput there available in channel 11. By default, when we configure the access points, or when the access points receive their default configuration from the FortiGate, the transmit power for the radios are all set to 100%. So that's the default value, and 100% transmit power may not be ideal for your deployment or for all deployments. And transmit power on an access point can actually be quite high compared to the wireless devices that you put on the network. A high-powered access point might transmit at 23 dB or even 26 dB, whereas most wireless devices that you put on the network, like a laptop, for example, might transmit at only 14 dB, and an iPhone even less, maybe at 10 dB. And this introduces a two-way asymmetrical transmit power issue. So the device, the wireless device, might have signal and see the access point with a reasonable signal strength, but that device doesn't have the power to effectively send traffic back and reach the access point at a good signal strength. So what we recommend, or what I recommend when tuning the radios in the access points, is that we decrease the transmit power on the access points to more evenly match the transmit power on the devices that we're going to associate to the network. This is done, again, through the access point profile, and you'll see that there's simple slider bars. So you can leave the transmit power at manual, and then if you want to make a 50% cut on the power, you just slide the TX power bar over to 50%. I recommend cutting the 2.4 gigahertz power down to 50%, which is a 3 dB reduction, or maybe even down to 33%. This has the additional benefit, not just of balancing power between the access point and the wireless device, but it also makes the 5 gigahertz radio look more attractive in signal strength versus the 2.4. So you get multiple positive benefits from doing small reductions in the transmit power on the access point radios. Now that we've selected our access points and we've designed our AP placement, we've tuned our spectrum use and adjusted our power, what can we do to balance the load of wireless devices across our access points efficiently? The FortiGate wireless controller has two different load balancing features for this purpose. Those are frequency handoff and AP handoff. Frequency handoff we could also call band steering. How does the band steering work? When we enable frequency handoff on the access point, all the radios keep a table of all the wireless devices that they see within their range. And they keep a table of the capabilities of those devices. So they note if that device is sending probe requests in 2.4 gigahertz, and they note if that device is sending probe requests in 5 gigahertz. If that device tries to associate to a 2.4 gigahertz radio, the access point checks the capabilities table, and if that device only supports 2.4 gigahertz, the access point accepts the association request and lets it write on the network. If that device tries to associate on 2.4 gigahertz and the access point knows that it supports 5 gigahertz, it'll actually send an AP full response back to that device and then get the device to next associate on a 5 gigahertz radio so that you can get all the high performance 5 gigahertz devices on the 5 gigahertz radios, leaving the 2.4 gigahertz radios for the devices that only support 2.4 gigahertz. And again, the reason why this frequency handoff is critical is the significant performance difference between 2.4 gigahertz and 5 gigahertz. So a 5 gigahertz radio operating 802.11ax with an 80 megahertz wide channel might have up to a 2 gigabit per second data rate, whereas a 2.4 gigahertz radio doing 802.11n with a small 20 megahertz wide channel might provide only a 300 megabit per second data rate to that device. So you definitely want to get all the devices that support the high performance network on the 5 gigahertz spectrum and leave the 2.4 for the legacy devices that can't take advantage of the 5 gigahertz throughput. There's also the ability to tune these features and how they work. For example, you can determine at what threshold do I want to start load balancing clients from one access point to another. So do I want to wait until an access point has 30 devices on it to start load balancing with a nearby access point? Or do I want that to kick in at 20 devices or 15 devices? I can also set a handoff signal strength. So I'm only going to load balance to the next access point if the client has a signal strength of a certain strength to ensure that they have good performance on the next access point over versus the one they initially tried to associate to. After doing all this work, I want a method to be able to check my work, see how it's all working together and how it's operating. That visibility can be implemented using the map feature in the FortiGate. This feature allows me to import the floor plan similar to how I did it in Fortiplanner when I first planned the network. It doesn't let me draw the walls in, but it does allow me to import the floor plan, and then I can place all the access points that are managed by the FortiGate in the exact location. I deploy them in the building, and then I can display different information about the access points. So I can view all the channels that are currently in use across all these access points, and that'll tell me how well my DARP is working. Is my DARP making good choices, or are there still access points that are interfering with each other and on the same channel? I can display channel utilization across my entire deployment just by clicking on utilization here, and it'll show me how busy the frequency is in all my different channels in one easy to use map. I can see client count per access point and per radio, so I can get an idea of how well that client load balancing is working. It also shows me transmit power on each radio, so I can see after I made my power cuts what the exact transmit power is across all my access points. Now, now we can discuss tools for maximizing efficient use of the overall Wi-Fi airtime. Certain types of traffic in the wireless standard, broadcast packets and multicast packets per the standard need to get sent at the lowest data rate. So this means in a heavily used network, a large amount of broadcast and multicast traffic sent at the lowest data rate can seriously degrade the overall cell performance of that network. So the FortiGate wireless controller has several methods to remedy this situation. One option is a multicast or broadcast conversion. So the access point and the FortiGate can actually convert multicast or broadcast packets, which get sent at the lowest data rate, to unicast packets, and then send that same packet out at a much higher data rate. We can also eliminate certain broadcasts from the network. The access points can do proxy ARP and reduce the amount of ARP traffic on the network. We can eliminate unnecessary DHCP traffic on the network. And all this will result in a higher performance cell and higher data rates. Now there is a trade-off on the unicast the multicast to unicast conversion based on how many devices are actually receiving that multicast stream. If it's a small number, then converting the multicast to unicast and sending it at a high data rate will provide for a higher performance cell. If there's a very large number of devices, then sending out one slow multicast packet versus 100 higher speed unicast packets might not be more effective. So there's definitely a balancing act there that you need to be aware of to use that feature. Also, be aware of what applications are being used on your network and control your network. It's your network and you should be in control of it. Be application aware because your wireless controller is. Since we're passing all that wireless traffic through the FortiGate is fully aware of all the applications and can fingerprint the applications that are being used on the network. And then you can use the FortiGate to manage the applications that you're allowing on the wireless network. So you can allow or deny traffic based on specific application. If there's applications you don't want on the network, you can simply deny that application and devices won't be able to use it on the network. You can also traffic shape applications. So if there's an application that you want to allow on the network, but you don't want it to take more than X amount of bandwidth from the network, you can apply a traffic shaper to that application and be able to manage how much of your overall network is being consumed by that application. Before we move on to FortiSwitch best practices, let's review again how we beat our Wi-Fi challengers here. So low signal strength. We were able to beat low signal strength by planning our network and planning for performance and managing our transmit power settings to make sure we meet the high signal that we want throughout our deployment. We beat low data rates by planning for performance by using the correct access point, so using a 3x3 or 4x4 MIMO high performance access point. We beat low data rates by bonding channels together with 40 megahertz or 80 megahertz wide channels and 5 gigahertz and doing unicast conversion on our broadcast or multicast traffic. We beat interference by being aware of channel width and not using too large of a channel, maximizing our use of 5 gigahertz where we have a lot of channels, being aware of utilization, how busy the network is, and also using our automatic radio resource provisioning to reduce interference by selecting channels for us. And we beat old technology by using frequency handoff to get all the devices that support it on the 5 gigahertz, and using a 2 radio or 3 radio access point to get all the older devices on a 2.4 gigahertz radio and not have those devices bring down the performance of higher performance devices. Now let's talk a little bit about how we're going to interconnect those access points and the wireless network back to our switches. The FortiGate has a built-in switch controller, which allows it to manage FortiSwitches in a similar manner to how it manages your access points that we just discussed. This integrated switch controller and management feature is what we call FortiLink. FortiLink has several key advantages over third-party switch network or a network of FortiSwitches that are just deployed in standalone mode. When we use FortiLink, we enable the zero config deployment of FortiSwitches. So FortiSwitches can get deployed right out of the box without any configuration on the switch. You just power up a FortiSwitch, you plug it into a FortiGate directly or into another FortiSwitch, and that device detects the FortiGate, shows up on your FortiGate as a managed FortiSwitch where you can authorize it and join it into the network. With FortiLink and FortiSwitches, you never need to take a switch out of the box, connect a console cable to it, configure an IP interface, and then SSH to it, and start configuring that switch at the CLI. It all gets done through the FortiGates interface, similar to how you configure an access point. FortiLink allows for a universal port configuration, which we're going to discuss in depth in a few slides. The FortiLink can detect compromised devices and automatically quarantine a device at the switch port. So since the FortiGate firewall is managing the FortiSwitches, we're passing traffic through the FortiGate. The FortiGate can monitor that behavior. It can send it to FortiAnalyzer for analysis. FortiAnalyzer can determine if a device is acting maliciously, send that device ID to the FortiGate, and the FortiGate can automatically quarantine that device at the FortiSwitch port with no administrative effort whatsoever. FortiLink also allows for the simplified and automated switch configuration and management. So a great deal of what you configure manually on other switches gets done for you automatically with FortiLink. With FortiLink, it's simple to deploy a fairly complex level of redundancy, and we highly recommend deploying a highly redundant network. In this depiction here, at the very top of the network diagram, I have a pair of HA FortiGates. And these HA FortiGates are managing 4 FortiSwitches via FortiLink. The first level of switches down are a pair of core switches. And these switches are deployed in what we call an MC-lag pair, multi-chassis link aggregation. And they look to any device connected to both these switches to be a single switch. So to my HA FortiGates, or to my 2 edge switches at the bottom, the MC-lag core switches appear to be a single 96-port core switch rather than 2 48-port independent switches. I connect both the core switches to each FortiGate. I connect them to each other. And then my edge switches, I connect a link back to each of the core switches. And then I can connect a couple access points. And if those access points have redundant interfaces, I can do link aggregation from my edge switch to my access point and add redundancy to the access point connection as well. This architecture with MC-lag actually reduces spanning tree use. All of these links are going to be active. So they're not only providing redundancy, they're also providing aggregated throughput. So I'm not using spanning tree in this architecture to have an active link and a backup link that's discarding, waiting for the active link to go down before it kicks in. I have a full, active, link aggregated, redundant network here, and it was very easy to deploy it with FortiLink. This architecture with FortiLink may be a little different than your current network architecture, where your routing may be at the core switches and you're passing internet-bound traffic up from the core switches through the firewall, FortiGate or otherwise, and out to the internet. In a FortiLink network, the FortiSwitches here, my core and my edge switches, are doing layer 2, and then all the routing and firewalling, all the layer 3 and above, gets done at the FortiGate. And since this is the case, when I'm deploying a FortiLink network of FortiSwitches, I need to make sure that I right size the FortiGate. So the FortiGate's not just a firewall, it might be managing my switches, managing my access points, doing all my north-south and east-west routing, and I need to plan appropriately for that. Here I selected a few popular FortiGate models in this table, and I noted how many FortiSwitches they can manage, how many access points they can manage, and what their firewall throughput is, and you keep that in mind for your routing. You see as we go up to the FortiGate 101F, and that's the first FortiGate where we introduce a pair of 10 gigabit per second interfaces on that FortiGate 101F model, and I can link aggregate those two 10 gig interfaces as my FortiLink interface to manage my pair of core switches, so I can deploy 10 gig switches in the core and get 20 gigabit of throughput from my core switches back to a FortiGate, even as small as a 101F. As we go up through the larger FortiGates, you see the firewall throughput dramatically increases. The number of managed access points goes from hundreds to thousands, and the number of managed FortiSwitches on a FortiGate 1101E is 196. So we can right size the deployment through planning to get the right number of switches and access points and the right size FortiGate to use. Excuse me. The FortiLink and the FortiGate integration also allows me to deploy a highly secure zero trust network. What this means when I configure my FortiSwitch ports is I can configure what we call a universal port configuration. So all my switch ports are configured exactly the same. They're not configured based on what type of device I'm going to plug in. So I don't need to configure a port for access points, a port for a VoIP phone, another port for laptops and desktop PCs. I can create a single port configuration. In this case, the default native VLAN on those ports is set to an onboarding VLAN. And what this onboarding VLAN does is it simply facilitates the ability of the FortiGate to detect what type of device I've plugged into that port. So the device will connect to the onboarding VLAN. It'll request an IP address. The onboarding VLAN will assign the device an IP address on the onboarding VLAN. It'll do its device discovery on that device. And then once it identifies, in my case, that I've connected a Forti-Access point to this port, it will apply dynamically a pre-configured access point port profile that I've configured for access points. So here you see port 5. It detected I had connected an access point to it. It toggled the native VLAN to my AP management VLAN, and then it added my data VLAN to the allowed VLANs. So my access point is tagging that SSID, so I need to add that VLAN as an allowed VLAN on that network. This happens automatically, so I can define the different types of devices that are going to be on the network, plug them into any port, and the FortiSwitch will configure itself for that device type. Any device type that's unknown or doesn't meet those device type definitions is going to sit in that onboarding VLAN where it can't harm my network or any other devices on the network. That's everything for the presentation today. Thank you very much for joining. I appreciate the opportunity to present this to you. My email address, eschulhoff@fortinet.com. Soraya's email address also included. If you have any questions about this material or anything else related to integrated secure access, FortiSwitches, Forti-Access Points, Forti extenders, please feel free to jot down my email address and shoot me an email. Thank you very much. Soraya?
Thank you so much, Eric. I hope everybody found value in today's presentation. Like Eric had mentioned, if there are any unresolved questions or you just want to learn a little bit more, please don't hesitate to reach out to either of us or your Fortinet account team. This session was recorded and a recording will be sent to you later this week. Again, thank you everybody for your time, and we look forward to seeing you again on future webinars. Have a great rest of your week. Take care.